it's time for us to do some problems involving dot product. And dot is something that's really important to know because dot products are going to be a great way of understanding how vectors relate to one another and useful for testing if things are orthogonal, doing projections, finding angles, all sorts of fun applications. So it's important dot we do the work. So you should try to do as many of these problems as you can. If you're following along, consider making frequent use of that pause button. If you see a problem, try it yourself first, and then if you need me, I'll come along and join you. And eventually, pretty soon you won't need me anymore. I'll miss you. Send me letters to let me know how you're doing. But for now, let's go ahead and get started together. So let's begin. Our very first problem. Find u dot v, so the dot product, given we have our picture here. The magnitude of u is 3, so that has length 3. Magnitude of v is 2, and there's this angle here, which is 3/4 pi. We say, this is really testing our geometrical understanding of dot product. We know that there's a nice geometrical interpretation of dot product. U dot v is the magnitude of u, magnitude of v, times cosine of the angle. So it seems like we have everything we need. So we have 3, because that's the magnitude of u, root 2, because that's the magnitude of v, and then we have cosine of our angle, right? And so what's our angle? And why is it not 3 pi fourths? Now you're probably looking at that and saying, that's our angle. It's 3 pi fourths. What are you talking about? That's not our angle. Look at the picture closely. Look at how these two vectors are connected together. In particular, you see I start u there, and then I end v, and then as soon as I start u and end u, and then I start v and end v. Their tails, their starts are not together. So the 3 pi over 4 is the wrong angle. You see, what we really need to do is we should take this vector u and we should just sort of push it over. So we want to push u so that when we think about these two vectors, they'd start from a common point. So if we push u to the side, and we say, okay, here's our new vector u. Really, you shouldn't call it a new vector u. It's just u in a better location. Now, what can we say about the angle? Well, here we see that this angle is 3 pi over 4. So this angle here, well, since it's the same u, the total here would be pi. We've already gone 3 pi over 4. So this should really be pi over 4. And therefore, when we take the cosine, we got to make sure we take the cosine of the right angle. You see, if we had taken cosine of 3 pi over 4, lo and behold, we would have been off by a minus sign. Because the difference between cosine of pi over 4 and cosine 3 over pi over 4 is a negative. So this is really be careful, be careful. Remember how we think about the angle. When we talk about the angle between vectors, it's if we put their ends together. So if their ends aren't together, well, be careful about what the angle is. You got to watch out. Well, what is cosine of pi over 4? Well, it is 1 over root 2. And so you see that the root 2, 1 over root 2 cancel. And we end up with 3, positive 3. So there we go. That's our answer. Now, on a side note, since this one went pretty quick, one of the things you can talk about in terms of dot product is you can actually say something about the value of a dot product. So you have, if u dot v is 0, then that means that they're perpendicular. In other words, you should really think of these as being at right angles. When u dot v is positive, well, what that means is that they are an acute angle. In other words, the angle that's formed is less than 90 degrees. So that they're pointing fairly similar direction. And when u dot v is negative, that means it's an obtuse angle. And by that, we say, well, look, they're actually pointing somewhat away from each other. So they're doing something like that. So that's something that we can figure out. So just by looking at the sign, we get some information. Are they pointing more or less in the same or more or less opposite type direction? All right, well, good. Let's try another problem. Find cosine of theta, where theta is the angle between the vectors 1, 2, -2, and 4, 0, 3. All right, well, the cosine of theta, there's this nice rule. And it says that because, cosine theta is related to dot product, you can use the dot product to find cosine theta. So cosine of theta is equal to our vector u dot v. Divide that by the magnitude of u times the magnitude of v. And that's true for any vectors. And again, any dimension you want. See, dot product is a beautiful thing. Works in, 3 dimensions, 2 dimensions, 18 dimensions. You pick a number of dimensions, it works there. So we take our 2 vectors, 1, 2, -2, dot, 4, 0, 3, and then we divide by the magnitude, 1, 2, -2, and the magnitude of 4, 0, 3. Well, dot products are easy. Go entry by entry. 1 times 4, 4. 2 times 0, 0. Minus 2 times 3, -6. Over, downstairs, well, the square root of each entry. 1 plus 2 squared, 4. -2 squared, still 4. And then there's also a square root of 16. That's 4 squared, 0, 0 squared, and 9, 3 squared. All right, so 4 plus 0 minus 6, -2. 1 plus 4 plus 4 is 9. Square root of 9 is 3. 16 plus 0 plus 9, 25. Square root of 25 is 5. And so we end up with -2 over 15. And we're done. Because we found cosine theta. Now, if we would wanted to find theta, then we say, well, take the arc cosine of that number. Well, that sounds like something we need a calculator for. So oftentimes we say, well, let's just be satisfied with finding cosine theta. So we're satisfied because we found our answer. All right, well, let's try some more problems. So on to our next one. Determine all values a so that the vectors a squared minus a minus 1, comma a squared, comma 2 minus a, and 2a, comma 3 minus 2a, comma minus 1 are orthogonal. So when we start seeing words like orthogonal, we should start sort of saying in the back of our head, hey, orthogonal means something. So we should sort of start substituting, all right, when we think orthogonal, we say, well, one of the things that's true, it doesn't mean it's always going to be what we need, but we build a collection of facts. So orthogonal says, hey, one of the things where orthogonal showed up was saying the dot product is 0. So we say, okay. So if I want these two vectors to be orthogonal, I just need to take their dot product and set it equal to 0. So that's what we should do. So we're going to say, well, we need 0 equal to a squared minus a minus 1, comma, a squared, comma, 2 minus a, dot, 2a, 3 minus 2a, and minus 1. So, for dot product, we just multiply the first entries, the second entries, the third entries, add things all together. So we're going to get a squared minus a minus 1 times 2a plus a squared times 3 minus 2a plus 2 minus a times -1. Okay, well, we keep working it out. We'll distribute here and expand. So we'll get 2a cubed. Ooh, we get to do a cubic. Minus 2a squared minus 2a. Then we'll get 3a squared. And then here there's a minus 2a cubed. Then we have a minus 2 and a plus a. All right, good. Well, progress, right? Now what we have is a polynomial equals 0. So we've reduced the problem to saying, hey, when does this polynomial equal 0? We could do that. So we just have to clean this polynomial up. Now we see there's a couple of things that are pretty easy to clean up. For example, our 2a cubes actually cancel, meaning we don't actually get to do a cubic. Well, maybe another day. But what else happens? Well, we have a minus 2a squared and a plus 3a squared, which just reduces to a squared. Minus 2a plus a minus a. Minus 2 minus 2. And so we say, all right, so we need a squared minus a minus 2 equals 0. Well, we probably can factor that. Indeed, after you've done these for a while, you're like, hey, we see certain polynomials showing up again and again. This one looks like something that can factor. We were looking for two numbers that multiply to give negative 2, add to give negative 1. Well, negative 2, there's not many things you can do. It has to be 2 and 1. And so we say, well, negative 2 and positive 1 have that property. So that would be what? So that would be a minus 2, a plus 1. And you can check. You get the a squared plus a minus 2a is minus a and minus 2. And remember, that equals 0. So that says that either a minus 2 equals 0, which would happen if a equals 2, or a plus 1 equals 0, which says a is negative 1. So we can come to the conclusion there's exactly two values for a. So here we get a is 2 and negative 1 as our two all values, the only values that work. So that those two vectors are orthogonal. Okay. All right. Interesting. Interesting. Good. Well, let's try another one. Okay. So find the projection of the vector u minus I plus 5j plus 3k onto the vector v minus I plus j minus 3k, and also find the portion of u which is perpendicular to v. So in other words, what we're doing is we're going to break our vector u, which points in some direction. Here's to say our vector v, which points in some direction. We're going to say, well, u is a little bit of v and something perpendicular to v. Okay, so that's what we're after. Really, once you have a projection, it's easy to find the perpendicular part. It sort of says, what's left? Take out the perpendicular part, whatever's left over, that's the part that you're looking for. So this is all about projection. Now, let's note something here. Notice how they've given us the vectors as minus I plus 5j plus 3k. You'll see this happen where they can give our vectors in different forms. They might say a vector which goes from this point to that point, then you have to create a vector. They might give a vector in component form, which is what you see when you have those angled brackets, and you see a list of numbers, Or they might write it in this format, minus I plus 5j plus 3k. Be comfortable in being able to recognize vectors in any form. Now, if you prefer one form over the other, that's perfectly fine. Just switch it to the form that you need. So we could, for instance, if we wanted to say, well, we could write this as u, another way is as minus 1, 5, 3, and as v as minus 1, 1, minus 3. We can go back and forth between these different forms. It doesn't matter which form we use. It's just a matter of representation. And so you want to use the form that you're comfortable with. So use what you're comfortable with. I tend to like things in component forms because it makes me feel like I'm being more algebra. And I like algebra. Algebra's fun. So let's talk about our projection. So whenever we're doing projection, we have to remind ourselves, well, it's the projection of one vector onto another vector. So we got to keep track. Okay, so which vector are we projecting onto? And so that should be very clear. So we're going onto v. So when we're interested in the projection of the vector u onto v, so that's this notation here. Well, what is that? It's u dot v over v dot v times the vector v. In essence, you can think of it as when I'm done, I should end up with something that's parallel to v. In other words, it should be a multiple of v. So we say, well, to be a multiple of v, well, there's v, and here's what I scale v by to get the right amount. So that makes sense. All right, so we just have to do some computations here. So in our case, we say, all right, well, we're going to take -1, 5, 3, dot with -1, 1, -3, over -1, 1, -3, dot -1, 1, -3. Okay, and then times this vector on the end. All right, there we go. There we go. Just to sort of emphasize what connects with what. So now we're just going to patiently work through. Be careful, and it'll be not so bad. -1 times -1 is 1. 5 times 1 is 5. 3 minus 3, -9. Downstairs, -1 times -1 is 1. 1 times 1, 1. -3 times -3 is 9. Good. So 1 plus 1 plus 9. Downstairs, 1 plus 5 minus 9. Upstairs, and of course that's multiplied by -1, 1, -3. All right, so we're almost there. 1 plus 5, 6, minus 9 is -3. So -3, 1 plus 1 plus 9 is 11. So minus 3 elevenths, minus 1, 1, minus 3. Or if you wanted to, you could multiply this through, which is perfectly fine. We can do that. So we end up with 3 over 11, comma, -3 over 11, comma, 9 over 11. All right, so this is our projection. Okay, now, if we were just asked about projection, we'd be done. But you'll notice this question also has the word also. It's right there, also, which means a little bit more work. It says, look, what's the part of u perpendicular to v? Well, the answer is you take your vector u, so the perpendicular part, because you would take your u, -1, 5, 3, and now you're going to subtract your projection. You're going to subtract 3 over 11, -3 over 11, and 9 over 11. So we're taking u and we're pulling out the part that's in the direction of v. Whatever's left has to automatically be perpendicular. Now, what can we do? Well, we can just think of this entry by entry, so put things into 11ths. So this is minus 11 over 11, subtract 3 over 11, comma, here would be 55 over 11, subtract -3 over 11, so plus 3 over 11, and then it would be 3, which is 33 over 11, subtract 9 over 11. And so we end up with minus 11 minus 3 is minus 14 over 11. 55 plus 3 is 58 over 11. 33 minus 9 is 24 over 11. And there we go. So this is the perpendicular part. So our projection and our perpendicular part. And we're done. We're done. Now, one of the things that we could do is, if we were really patient, we could say, can we check? Well, how would we check? One way to check is to say, these two pieces here should be perpendicular to one another, because one part is in the direction of v, one part is perpendicular to v. So if you have two vectors which should be perpendicular, what should be true is their dot product should be 0. Now this one is probably not an easy one to do where we compute the dot product. So for example, 3 times -14, that's -42. -3 times 58, that's -174. So you have -42, -174, that's -216. 9 times 24 is positive 216, and therefore when you put it all together, the dot product is indeed 0. So, whew, okay, we did something right. So that's a good sign. All right, well, let's do one last problem. One last little cool down problem. Okay, so here we go. So we have a vector w. So what is it? W is the projection of u onto v. So what do we have? Well, we have some vectors. We'll just sort of think of our basic picture. Here's v, and we'll say here is u. And now we have w, which is our projection of u onto v. So w says it'll be right here. All right, so there's our projection. Then there's the question. What is the projection of w onto v? Okay. Well, we can approach this in two ways. We can think of it geometrically, or we can do it algebraically. Let's try to do it geometrically, because algebraically I think it'll be a little bit of a morass. Well, if we have some time, we'll do it algebraically as well. So let's think about what projection is asking. Projection asks the question, how much of the vector currently points in the direction that I'm projecting onto? So, for instance, when I'm talking about the projection of u onto v, how much of u is pointing in the direction of v? And when I say in the direction of parallel to. All right. So once I've done the projection, whatever the output is parallel to what I was projected onto. So we know w points parallel to v. So we can think of it as w as being more or less in the same direction. Now, I come to the next question. What's the projection of w onto v? Well, the question is, how much of w points parallel to v, or if you like, in the direction of v? Well, the answer is all of w points in the direction of v, because the projection automatically gives us that what we projected onto v, so we're already pointing in v, everything is pointing in the direction of v. So if the answer is everything's already pointing in the direction the right way, well, what's the projection do? The answer is it just says, hey, you're already great. We like you just the way you are. We don't have to change anything about you. You're already going in the right direction. You've made good choices in your life. And therefore, because we're already pointing in the direction of v, our projection says, no change needed. Here you go, back to where you began. So that's one thing to keep in mind. If I'm projecting onto a vector, and it's the case that I'm already pointing in that direction, the projection will just return what I began with. All right, so that's the geometrical argument. What if we wanted to go through and do the algebraic argument? All right, well, I like geometric when we can. When I do that, you might think, what? Steve doesn't like algebra? It's so unlike him. No, it's not that I don't like algebra. It's just sort of like, I love geometry also. And sometimes there's a beautiful geometric argument that when you see it, you're like, so beautiful. Okay, so here's what we can do. We know what w is. W is u dot v over v dot v times v, because that's the formula for a projection. All right, so now what we're going to do is we're going to take this and plug it into our projection. So we're looking for the projection onto the vector v of u dot v over v dot v times v. Okay, so that's the projection of w. So the rule says what you do is you take your projection, whatever you're projecting down, so it'd be this u dot v over v dot v times v, and then we're going to dot that with v. and you're going to divide that by v dot v, and all of that times v. So that's simply saying, take this formula and put it into the projection formula. Okay, now what should be true? What should be true is things should simplify. So what can we do? Well, actually, the key thing is going to happen in the numerator. So if we just keep track of what happens up here, you'll see something really lovely happens. This is a constant, so I have a constant times v dot v. So up in the numerator, it becomes u dot v over v dot v times v dot v. And then downstairs, I see a v dot v and times v. And now we say, aha, perfect. The v dot v's cancel. And what are we left with? Well, we're left with u dot v over v dot v times v. And at this point, we say, well, wait a second. This result exactly matches with what went in, which means that when we plug w into the projection formula, we got w back out. So that's what we mean when we say, look, it doesn't change anything. If we're pointing in the same direction, we're already good to go. Life is good. Life is good. All right, and that's actually our last problem for this practice session. Of course, come back because we'll do more practice, and the more we do, the better we come. And dot is something you should remember. Have a great day.